In this video, we're going to be going over the binary search tree data structure, and I'd recommend if you have not seen the series on just binary trees on this channel, at least the first video in that series, I'd recommend that you watch that first video first, just because in that video I'm going to be going over a lot of the general terminology that one encounters when one looks at tree data structures, such as what a root is, traversals, nodes, those sorts of things. If you're familiar with that type of terminology, then you can skip watching that video and you can just continue on with this binary search tree video. If those concepts are new to you, I'd recommend that you watch that video first before watching this binary search tree video. So with that said, let me just go on and define what a binary search tree is. So again, assuming that you've seen the binary tree video or you know what a binary tree is, a binary search tree is really just a tree data structure that each node has at most 2 children. So that's where the term binary comes from, for 2 children for each node. And then we typically refer to the children of every node as the left and right child of that node. So this one is the left child of this node consisting of 8, and this node with data element 10 is the right child of this node here, which in this case is the root. So the way that binary search trees differ from binary trees is that there's some form of order imposed on the nodes, on the elements in each of the nodes in the tree. So in this case, we have that each of the elements in this tree are sorted. So specifically, the root here has element 8, and then the left child of any node in this tree will be lesser than whatever value we have in this node, and then the right child of whatever value we have here in this node will be greater. So for instance, this value is 8. To the left, we have 3, that's less than 8, and then 10 we have to the right, which is greater than 8. So this type of pattern persists all throughout the tree. So for instance, if we look at this node here, which contains the data element 3, the node to the left of 3, the left child of 3 is 1, that's less than 3, and then likewise the child to the right of 3 is element 6, and that is greater than 3. So this, again, this pattern persists all throughout that tree, and that's what makes this particular tree a binary search tree. So let's take a look at insertion in a binary search tree, and we're going to take a look at an example. We're going to assume that we have this, let's say, array of elements, array of numbers in this case, that are given to us, and what we want to do is we want to take each of these elements and form a binary search tree out of the elements that were given. So what we can do is we can start, let's say this is the beginning of the array, and we start from the beginning and we process all the way to the end. So we look at the first element, which is 8, and our tree right now is empty. There's no element in our tree. So this 8 is going to, by default, be the root of our tree. So I'm just going to denote that here by this circle, which is the root node of this tree. So that's all we need to do in this case. So let's move on to the next element in the array that we're going to process, which is 3. And the way that we insert into a binary search tree to make sure that the order is maintained is we start from the root and we check, is the element that we're about to insert, is it greater than this element here or is it less than? And then we just keep asking these questions until we find the appropriate place to put the data element. So in this case, we have 3. We look at this root 8. So 8 is greater than 3, so we know that any element that's going to be less than 8 in this case, which is 3, it needs to go to the left of this node with 8. So what we do is we take out 3, and it goes to the left of this node here. So this is now the left child of this root node 8. So we follow a similar pattern with remaining elements as well. So the next element that we have is this element 10. We start here at the root, and we ask, is 10 less or greater than this element here? So 10 is greater than 8, so we know that we need to check the right. There's no node here on the right, so what we do is we go ahead and we create a node, and that's where we put this node 10. So 10 now lives as the right child of this root node. So we follow through, we have 1 here, so we start here at the root, we ask, is 1 lesser or greater than 8? So 1 is lesser than 8, so we move to the left. And we see that there's a node here, so we ask the same question. We ask, is 1 greater than or less than this element stored at this node here, 3? So it's less. So we go to the left. We see that there's no node here. So we go ahead and create a node, which is the node that will store 1. So that's where 1 will go. And then we do the same thing for 6. Figure out where 6 goes. We start at 8. 6 is less than 8, so we move to the left. 6 is greater than 3, so we move to the right. We notice there's nothing there, so 6 goes right there. So we have here just our binary search tree. So let me just go through another example of insertion where the elements in the array that were given are given to us in reverse sorted order. So we have the same elements we had before, only this time we have them in reverse sorted order. So 10, 8, 6, 3, and 1. So let's see what this tree looks like if we try to form a tree out of this array sorted in this fashion. So what we do is we start again at the beginning of the list. We take out 10. It's the only element in our tree, so that just becomes the root node of our tree. So that's where 10 is. We check now 8. So 8, we look at where that should go in this tree. So we start off at 10. 8 is less than 10. So we check if there's anything to the left. There's nothing there. So we go ahead and we put 8 to the left of 10. So we do the same thing for 6 as well. We take out 6. We ask, okay, well, 6 is less than 10. 6 is less than 8. There's nothing to the left of 8, so that's where that goes. And you can kind of see where this is going. You're essentially going to get a list-like data structure. So the whole purpose and the whole benefit of a binary search tree is the structure of that tree. And specifically, that structure of the tree is going to allow you, when we see searching in a little bit, it's going to allow you to essentially eliminate various parts of the search space to find an element in the tree. And if your tree looks like this, there's not much you can eliminate. You basically just have the same benefit that you would have in a list. So if you want to search for an element in this tree here, you're going to have to traverse the entire all of the nodes in this tree in the worst case. So for instance, if you wanted to find 1, you would have to start at 10 here. There's nothing to the right, so you would have to go to the left. 1 is less than 8, 1 is less than 6, 1 is less than 3, and then you'd eventually arrive here. But if you had a structure like this, then what you could do by taking advantage of the binary search tree structure is you can essentially cut down the number of operations that you would have to do to find that element 1 in half. And we're going to see specifically what that looks like when we cover searching. So this is kind of sort of a structure that we want to avoid, and it's beyond the scope of this video. But if you're curious about how you can kind of avoid getting this structure from reading data and forming a binary search tree out of this, then you can look into something called an AVL tree. So this is going to sort of rebalance the nodes in a way that you still get this structure that is beneficial to the binary search tree data structure, and that is just going to be, again, beyond the scope of this video, so you can look up the Wikipedia article on that. We may cover that subject in a future video. So let's take a look at how we can search for an element in a binary search tree. So let's assume that this is our tree here, so there's a few more elements in this tree, and actually I've gone ahead and filled out the nodes. So every single node in this tree has 2 children with the exception of the leaves. So this is what is known as a complete binary search tree. So we covered different types of trees in the binary tree video, and one of the types of trees that we covered was a complete tree. So if you want to refresh on that, again, just consult that video. So let's say that we're given this tree and we want to search for an element in this binary search tree. So we want to search for 1 in this case. So what we do is we know that the binary search tree has a particular order imposed on it. So what we can do is we start at the root and then we ask subsequent questions. We ask, is the element that we're looking for greater than or less than the value that we're currently on? So we know that 1 is less than 8. So we know that the 1, if it exists in the tree at all, is going to be in this portion of the tree. So we go ahead and move on to the left child of the tree. And you'll notice that all of these nodes in red essentially indicate the search space that we're eliminating. So we know that the node 1, the node that contains data element 1, cannot be in any of these nodes. So we sort of eliminated all of the elements in this tree, and if the tree is particularly large, you're eliminating quite a large chunk of the tree. So we're going to continue on in this way. We're at 3. We're still searching for 1. And so we ask, is 1 less than or greater than 3? Well, 1 is less than 3. So again, we cut our search space and we go to the left, since we know that 1 is going to be, if it exists at all, to the left of 3. So we move to the left, and in this case, we find 1, and that is the end of the search. So again, if we had a tree that looked like this, where this is really more like a list, if we wanted to search for the element 1 in this type of tree, what we would end up doing is we would start at the root, and then we would say, okay, 1 is less than 10, so go ahead and go to the left. 1 is less than 8, go to the left. Go to the left, and then we'd eventually arrive at 1, but this operation is going to take linear time, where the linear operation is with respect to the size of the tree or the number of nodes in the tree, and this is not going to give us anything better than traversing a list. So it's just kind of a summary. Here is the time complexity of various operations that you can perform on a binary search tree. So let's just go over each of these one by one. So the space, if you want to store n things, let's say n number of nodes you want to store in this binary search tree, of course, the worst and average cases, you're going to have to allocate n nodes. You really can't get away with allocating less than n nodes if you want to store n things. So the average and worst case is going to give you big O of n. Search, we saw that the best case is you're going to have a tree structure that looks like this, sort of a complete binary search tree, and in the event where you want to find an element in that tree, you're subsequently eliminating half of your search space on every move to the next node. So that is kind of a reverse exponential. It's one way to think of it, and that is going to give you a logarithmic search time. So the time that you find a node in a tree of this form is going to be log of n, where again n is the number of nodes in your tree. Of course, you could have a binary tree that looks like a list, and in that case the worst case scenario is going to be a big O of n, so it's going to involve traversing every single element in the list before you actually, or in the tree, before you get to the element that you're after. So there's a similar type of story here with insertion. So if you want to insert in this tree, say, then all you would have to do is find the position in which to insert your node. So if you wanted to insert, let's say, the node 0, you could start up here at 8. And this is a similar type of idea for why it's a logarithmic time for searching as it is for insertion. You go start from here, 0 is less than 8, less than 3, less than 1, and then you found the position where you want to put in the node with element 0. Whereas if you had a tree structure that looks like this, where it's essentially no better than a list, then the amount of time that it would take you to find where to insert the node with 0 would involve you to traverse every one of these nodes, and then eventually you'd end up here where you know that 0 would go to the left of this element with 1. So that's where the big O of n with the worst case there comes from. And then finally, deletion, which we have not covered in this video, but we will cover in a subsequent video, has a similar runtime analysis for both on average and worst case, and the logic there for log n and n is very similar to what we saw for search and insertion. So now that we've got kind of an idea of how a binary search tree is formed, how it's structured, how to perform search and insertion operations, we're going to go ahead and take a look at how to implement this data structure in Python. So now that we're in our text editor here, we're going to go ahead and code up the binary search tree implementation in Python, and we're also going to code up the search or find and insert functions as well that we went over in the slides. And just like we did for the binary tree Python implementation, if you saw that video, we had two classes. One was a class for the node objects that are stored in the tree, and the other is for the tree itself. So we'll be following a similar pattern for this implementation here as well. So let's start off by creating the node class for the binary search tree. We'll call this class node, and in the constructor of this class, it'll take self, since this is of course a function for this class, and then also the data element that will be stored for this particular node. So by default, we'll just set that initially to none, but we'll pass in some element, some number in this case, which will be the data that will be stored at that node. So we'll set the class variable self.data equal to whatever's passed into this constructor. And then of course every node is also going to have both a left and right child as well. If we don't specify what those are just going to be equal to initially none. So we'll say self.left, which corresponds to the left child, equal to none, and self.right is equal to none as well. So that's all we really need for the node class. So now we're going to go on to the binary search tree class. So we'll say class BST, and in the constructor of this class, all we really need to do is just define the root node of the tree. So initially that root node won't have any contents in it whatsoever, it'll just be empty. So we'll just go ahead and set the root variable for this particular instantiation of the binary search tree equal to none. And that's all we need to do in the constructor. So now let's go ahead and implement the find method and also the insert method for the binary search tree. So let's start off with insert. We'll call this method insert. So this is going to take self, it's a member of the class, and it's also going to take the data. So this is going to be the node that we're going to construct based on the data that we're given, and we're going to insert that into the tree. And since we're dealing with a binary search tree, we need to make sure that we insert that node in the appropriate position in the tree that we've constructed. So what we're going to do first is we're going to check two things. First, we're going to check whether or not the root node is none, because if there's nothing in the tree, the root is set to none, then the variable that we're given, the data that we're given, we're just going to construct a node based on that and set the root equal to that node that we've constructed. So we'll take care of that case. If self.root is none, then what we're going to do is we're going to construct a node, and we'll do that by node of data, and we'll set the root of the tree, so self.root is just equal to this node that we've constructed based on the data that we were given. So in the other case, the tree has at least one node in it, possibly more, and we need to find the appropriate location that this new node that we're going to construct should be placed. So else, what we're going to do is we're going to insert this new node. And what we're going to do, our approach, is we're going to create a helper method that will distinguish from insert by putting an underscore in front of it. So it'll be called underscore insert. And this is going to really do the dirty work of actually finding where the appropriate location is where this new node should be inserted. And it's going to do so in a recursive manner. So it's going to start at the root, just like we saw in the slides, and it's going to ask whether or not the data that we're given is less than that node or greater than. And then depending on that answer, it's going to follow the path appropriately. So if the data is less than the node that we're currently looking at, we're going to go to the left, because that is where that new node should be placed in the binary search tree to make sure that the order aspect of that binary search tree is maintained. So what we're going to do here is we're going to call this method, which we will eventually write, self.underscore-insert. It'll take the data that we want to actually insert, and then we'll start off by putting the root. So this is going to be the start of where we're going to be looking where to put this new node, and then as we move through these recursive calls, we're going to move through from the root to the different nodes in the tree until we find the appropriate location to put this new node at. So let's go ahead and implement the underscore insert method. So this will take self, it'll take the data that we want to insert, and then we'll also take the current node. So again, this is going to be, kind of where we are in the tree as we move along, and we check whether or not the value of the current node is less than or greater than the value that we're given that we want to insert into the tree. So what we're going to do here is we're going to check if the data that we're given is less than current node data. So if this is the case, let's say the current node has value 8 and the data that we want to insert maybe has value 1. So this is the case that would hit this if statement here. And if that is the case, what we want to do is we know that the place where we need to insert this node is going to be to the left of the current node. So the current node has value 8. We have value 1. We need to move to the left. So what we're going to do is we're going to move to the left, but we want to check first before we do that if the left child of the current node is none. Because if the current node's left child is none, that's where this data is going to go. We're going to construct a new node based on the data that we're given, and the left child of the node that we're currently on is going to be this data. So if current node dot left is none, so there's no left child of the current node that we're on, we're going to go ahead and say current node dot left is equal to node data. So otherwise, let's say that the left child of the current node does actually have a left child. In that case, then we just want to move to the left and recursively call the insert function and then just kind of keep going throughout the tree. So otherwise, else, what we're going to do is we're going to say self.underscore-insert. So we're recursively calling this helper method with the data so that it doesn't change. And then we're going to move to the left because that is where we want to head, because that's where this data element should eventually go. So we're going to say current node dot left. So we're recursively calling this function with the left child of the current node. And then we have a very similar pattern for the other case where the data element is greater than the current node's data. So else if data is greater than current node dot data, in this case, we're going to do pretty much the same thing. If current node dot right this time is none, we're going to set current node dot right equal to the new node that we'll create based on the data that we're given. And then otherwise, we're going to say self.underscore-insert data and then current node, in this case, dot right. So that will do the same thing that we saw up here, only for the other case where the data element that we're given is greater than the current node's data. So otherwise, we're also going to have an else condition here where if neither of these two if statements are triggered, then the data element that we're given is equal to some element that's already in the tree. And in this case, we're not going to allow that. We don't want any duplicates in our binary search tree, so we're just going to go ahead and print out a message that says the value is already present in tree. So we're just going to print out that message. So we don't want any duplicate values in our binary search tree. Okay, so that's the insert method that's pretty much done. Let's go ahead and do the find or search method. So we'll call this find. So it'll take self, since this is also a function of the class, and then the element that we want to find, which is based on this data. So we want to find a node that has the data element data that we're putting into this function. And we're going to follow a very similar trajectory to what we did for insert. Namely, we're going to have a helper function, and this helper function is also going to be called in a recursive manner. And it's probably no surprise that there's going to be a bit of overlap between these two functions, because where we find the appropriate place to insert a node is going to be quite similar to where we find a given node is present in the tree. So it's going to have kind of a similar type of pattern structure to how we insert. So there should be some overlap here. So what we want to do is first we want to check if self.root. So if there is actually some content in the tree, if the root is not none, we're going to go ahead and apply a function which we'll call self._find. So this will be the helper method, much in the same way that we had the helper method for insertion. And this will take the data and also the root. So basically this function, what I assume it's going to do is it's going to return a Boolean variable, and that is going to let us know if the value is in the tree. It's going to be either true or false. So if the value is true, we know the value is in the tree. If it's false, it's not in the tree. So we're going to go ahead and fill in that function eventually. But then what we're going to do is take that isFound variable, and if isFound is true, we're going to return true. So we're going to return that the value is indeed in the tree. And otherwise, if that value is none, so if there's no true that's returned from that function, we're going to just return false. So we want an else condition for this self.root if statement here. So if there is no content in the tree, if there's no nodes in the tree, we're just going to return none because we can't find an element in an empty tree. So we're just going to return none there. Okay, so now we need to fill in this _find function. And again, it's going to be called in a recursive manner, much in the same way the _insert function was called. So let's define _find. It'll take self, the data that we're looking for, and we'll also call this current node. So this is going to serve a very similar purpose to what it did in insert. Namely, we're going to start at the root, and then we're going to ask, okay, is the element that we're searching for, is it less than the current node's data, or is it greater? Because then we'll have to traverse either to the left or to the right based on the way that we know the binary search trees are structured. So let's go ahead and just code that up. So what we'll do is we'll say if the data that we're given to search for is greater than the current node's data, and current node.write actually exists, because we want to not only see if the data is greater than the current node's value, but also if it has a right child. If it has a right child, then we'll go ahead and traverse there. We'll make a recursive call to this _find method with the right child of the current node. So what we're going to do is we're going to say return self._find, the data that we're given, and then also current node.write. So we're going to recursively call it with the right child of the current node because we know that the data that we're looking for must be on the right side. Likewise, what we're going to do is we're going to say if data is less than the current node.data and current node.left actually exists, that is, there is a node, there's a left child of the current node, we're going to return a recursive call self._find data, and then in this case we're going to say current node.left. And then what we're going to do is if we have the event where we stumble on a node where it's actually equal to the data that we're looking for, we're just going to return true. So if the data that we're given that we want to find in the tree is equal to self dot, or let's say current node dot data, we're just going to return true. So this will return true if this finds the data element, and otherwise if we just keep going through this tree, we're not going to find anything. This function will return none, and then we'll check if this is none. So if it's none, then we'll return false. Otherwise, if it is something, in this case it will return true if the variable is actually in the tree, then we'll return true as the element is present in the tree. So let's just go ahead and construct kind of a dummy binary search tree structure, and then put some elements in there by inserting them, and then see if we can find whether or not the elements are present in the tree. So let's say bst is equal to bst, and then we'll say bst.insert. Let's insert a couple elements here. 4, let's do maybe a few other ones. Let's do 2, let's do 8, and let's do 10. And that's, let's do 5 and 10. So 5, 10. Okay, so we've inserted some elements. Let's just go ahead and write that, clear the terminal, make sure that we actually don't get any errors or anything like that. So we'll say Python binary search tree, and we don't get any errors, so it seems like insertion happened as we expected, hopefully. And so now let's go ahead and try to see if we can apply our search method to the class that we have here. So we'll go ahead and go down and say bst.search or find, and then we're going to try to find an element in the tree. So let's go ahead and try to search for something we know that's in the binary search tree. So let's go ahead and search for 4. And I'm going to print this out because this is either going to return true or false. So we should get a value of true since we know that 4 is indeed in the tree. Let's go ahead and print that out to make sure. So we do get true. Let's go ahead and make sure that it sees 5. We know 5 is in the tree. We get true there. Let's go ahead and try 10. So it says true there. So let's try 11. So 11 is not present in the tree. So we get false because 11 is not present in the tree. So the find or search method appears to be working properly. So that pretty much does it for this video. In subsequent videos, we'll go over other applications of the binary search tree data structure. If you have any questions or comments or anything of the sort, just leave them in the comment section below, and I'll try to address them when I can. The code for all of this will be available on my GitHub, so if you want to download this and play around with it, you can follow the link in the description and download that code. So thanks again for watching, and have a nice day.